In this video, we'll be discussing the fundamental theorem of calculus, part 1. So let's start with an example. Let's see if we can find the integral from a to b of x squared. So a and b are just constants here. Okay, they're just fixed constants. But remember that we know what the integral from 0 to b is. We know it'll always be b cubed over 3. And we also know that the integral from 0 to a of x squared will be a cubed over 3. And using the properties of definite integrals, we know we can rewrite this as the sum of the integral from 0 to b and a to 0. And then we can change the limits of integration on the second integral. Right? And when we change the limits of integration, this becomes a negative sign or a minus sign. Okay, and we know what each of these pieces are. We know that this first one is b cubed over 3, and we know that the second one was going to be a cubed over 3. So why does this matter? Why is this interesting? Well, recall that x cubed over 3 is an antiderivative of x squared. So what really happened is if we define this to be f of x, we discovered that the integral from a to b of x squared dx was just f of b minus f of a, where f is an antiderivative of x squared. And you'll actually notice it doesn't matter which antiderivative we picked, if we picked x cubed over 3 or x cubed over 3 plus 1, as long as we were consistent about which one, because those constants would have canceled. So we call this the fundamental theorem of calculus because it's such an important theorem. It's really connecting integrals, these definite integrals in the area under the curve, with this idea of antiderivatives. Okay. So if we have a continuous function on the closed interval a to b, and if we have any antiderivative of a function lowercase f on this interval, then we know that the integral of that function will just be the difference of the antiderivative evaluated at the endpoints. So let's see if we can see why this would work. So we're not going to do an explicit proof, but we are going to sketch the proof. So let's consider a graph of our function big F. Okay, and let's suppose that we just have 2 points, say B and say A. And so here we have f of A, and here we have f of B. Okay, so let's look at f of B minus f of A. And we want to see if we can connect this to the integral. Okay, so f of B, okay, so f of B minus f of A is just this vertical distance here. Notice that if we partition the interval a to b into maybe n subintervals, so let's partition AB and we'll partition it with the points x0, x1, x2, all the way to xn, where xn is b and x0 is a. Then we have our f of x1, f of x2, f of x3, f of x4. And it might not always look this nice, but that's totally fine. It would work out no matter what, and we're just sketching a proof right now. Notice that I can rewrite f of b minus f of a by just taking the sum of the differences between maybe f of b and xn minus 1 plus f of xn minus 1 minus f of xn minus 2, right? So I'm just adding up all these little vertical distances to get this larger vertical distance. So I can rewrite this as f of xn minus f of xn minus 1 plus f of xn minus 1 minus f of xn minus 2 plus all the way down to f of x2 minus f of x1 plus f of x1 minus f of x0. Here, I'll write this a little bit clearer over here. Okay, so now we've written this a little bit clearer. So what we did is we just rewrote this difference here, which is this vertical distance, as the sum of these little differences. Okay? Those are these little differences, these little distances on our y-axis. But notice that for almost every single term, I'm both subtracting it and adding it, right? So that we know that this will be equal to just f of b, which is f of xn, minus f of a, which is f of x0. Right, so we're subtracting xn, f of xn, but we're also adding f of xn. We're subtracting f of xn minus 2, but we'll be adding it in the next term, etc. We'll be subtracting f of x2 in the ellipses here. We're subtracting f of x1 and then adding it, right? But we're never adding f of x1, and we're never subtracting f of xn, right? And remember, xn is equal to b, and x0 is equal to a. So we really do have just f of b minus f of a. Okay. So what we essentially just did is we just wrote f of b minus f of a as the sum of f of xi minus f of xi minus 1, where I is ranging from 1 to n. Okay, well, let's look at each of these individual pieces. This is here is giving us the slope of the secant line, right, between the points where x is equal to xi and x is equal to xi minus 1, right? So this is like this secant line, like right here, right? And recall that by the mean value theorem, this is equal to f prime of some point ci for ci in the interval xi minus 1 to xi. And this is by the mean value theorem. Okay. But recall that f is an antiderivative of little f of x. So f prime of x is equal to f of x. Okay. Okay, and then we can multiply over. So we can rewrite this as, well, f of xi minus f of xi minus 1 will be f of ci times xi minus 1. Let's let delta xi be the difference in these values. Then this is really just equal to f of ci times delta xi. And that looks really familiar, especially when we have the sum of all of these differences. So we essentially just have the sum f of ci times delta xi as I ranges from 1 to n. And recall that this is equal to f of b minus f of a. Okay. Well, this is a Riemann sum, and we know that if we take the limit as n approaches infinity of any Riemann sum, it will be equal to the definite integral. In this case, we actually chose our sample points, these values of c, such that we actually, this is strictly the integral. We don't need to take the limit as n goes to infinity, but we will anyways, just to kind of be thorough. So the limit as n approaches infinity of this Riemann sum, we know is just the integral from a to b of f of x with respect to x. So we did it. Right? We showed that this difference in the antiderivative is truly the integral of a continuous function. And we use the continuity when we did the mean value theorem. Okay? Let's see if we can try some examples. Let's evaluate the integral from 0 to 9 of the function e to the x. Recall this works for any antiderivative. I always like to pick the easiest antiderivative, so the one where that extra constant at the end is just 0. So we can say, well, f of x is equal to e to the x is an antiderivative of e to the x. So this will be equal to f of 9 minus f of 0, which is e to the 9 minus e to the 0, so e to the 9 minus 1. So sometimes writing this all out is a little bit tedious, especially if you have to define a function like this every time. So we have a special notation that we like to use. If we say something like the integral from 0 to 9 e to the x is equal to f of x, and then we put a little bar here, we say from 0 to 9, this means we're evaluating f at 9 and then subtracting f of 0. So we could say something like this is equal to e to the x evaluated from 0 to 9, and we would know that would mean e to the 9 minus e to the 0. Okay. So this is a notation thing that's really important because we're going to want to use it a lot. So if I have some function and I have that vertical bar, that means evaluate this function at b and then subtract the function evaluated at a. You may see it other times written like this, or even like that. Okay. But we like to use it when we're evaluating these integrals so we don't have to define this antiderivative every single time. Okay. Let's try the next example. Let's see if we can find the integral from -2 to 3 of x squared minus 3x plus x to the -2. Well, what's an antiderivative of this function? Well, we can look at each piece individually. The antiderivative of x squared, x cubed over 3, minus 3x squared over 2, plus x to the -1 over -1. And we're going to evaluate this from -2 to 3. Okay, so we'll get the same thing as if we evaluated, if we had maybe a different antiderivative, so if we had plus a constant, because we would be adding the constant when we evaluated the function at 3 and then subtracting it when we subtracted the function evaluated at -2. So here we'll have 3 cubed over 3 minus 3 times 3 squared over 2 minus 3 to the -1 minus this entire function evaluated at -2. So we have -2 cubed over 3 minus 3 times -2 squared over 2 minus -2 to the -1. So we get 1/3. Let's try another example. Let's evaluate the integral from 0 to pi of sine of 2x. Well, an antiderivative of sine of 2x is negative cosine of 2x over 2. And we'll be evaluating this from 0 to pi. So we have negative cosine of 2 pi over 2 minus negative cosine of 0 over 2. Well, cosine of 0 is 1, and cosine of 2 pi is 1. So here we have -1 over 2 minus -1 over 2. So we have 0. Now let's show that this didn't matter, that it didn't matter which antiderivative we picked. So let's say that we picked negative cosine of 2x over 2 plus some fixed constant c, and we evaluate this from 0 to pi. Well, then we're going to get negative cosine of 2 pi over 2 plus c minus negative cosine of 0 over 2 plus c. And those c's are going to cancel. So again, we'll just get negative cosine of 2 pi over 2 minus negative cosine of 0 over 2. Okay, so it doesn't matter which antiderivative you pick, as long as you pick exactly one, that you're not using a different antiderivative for evaluating different limits of integration. So like evaluating the pi and evaluating the 0. So see if you can give this a shot. Try these integrals here using the fundamental theorem of calculus part 1. And remember, you're finding the exact area under the curve here. It's just a nice shortcut.